The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
A classic application of Ampere's integral law is to the prediction of the magnetic field of a line current. Ampere's integral law states that the integral of the magnetic field intensity around a closed contour C is equal to the net current, conduction plus displacement, that passes through the surface S that is enclosed. The integral of the magnetic field intensity around a closed contour C is equal to the net current that passes through the surface S that is enclosed. In this demonstration, the current density and associated fields are at 60 Hertz. Because this frequency is low, the time rate of change is relatively small. As a result, the displacement current contribution to Ampere's law is negligible. In this demonstration, a line current essentially extends to minus and plus infinity. This line current passes through a surface S enclosed by this contour C. Ampere's law says that there is an integral of H around the contour C. Symmetry requires that only the azimuthal component of H be non-zero and that this component only depend on the radial position r. The line integral is simply the product of h phi and the circumference 2 pi r. The surface integral is the total current I. H phi is inversely proportional to r. H phi is proportional to I. In our experiment, the wire is horizontal. Here is the wire. Ampere's law predicts the magnetic field intensity as it depends on R. H sub phi is inversely proportional to R. This Hall effect probe measures the magnetic field intensity. The top trace on the oscilloscope is a measure of the probe output. The lower trace measures the wire current. The wire current is measured by measuring the voltage drop across a series 1 ohm resistor. We measure 6 volts peak, so the current is 6 amperes peak. This probe measures magnetic field intensities perpendicular to its flat surface. When aligned in this direction, it measures the z component of magnetic field, about 0. When aligned in this position, it measures the radial component of magnetic field, again about 0. When aligned in this position, it measures the phi component of magnetic field, which seems to be the only non-zero component of magnetic field. For a current of 6 amps, Ampere's integral law predicts this 1 over r radial dependence for h sub phi. Our measurements are limited to distances r, small, compared to the distances to the end of the wires or to the return wires below. Because the Hall effect probe fundamentally exploits the Lorentz force law, it measures the flux density mu naught h. A common unit for flux density is the Gauss. We have to take this into account in evaluating Ampere's law. For conversion of units, 10,000 Gauss equal 1 Tesla, where the Tesla is the SI unit. With the probe at 1 centimeter, the measured flux density is 1.2 Gauss peak. I is 6 amps. R is 1 centimeter. So we calculate mu naught h phi to be 1.2 Gauss. Here is the data point on our plot. Here are some other measured values. We have demonstrated the relationship between current through a surface S and magnetic field intensity integrated around the contour C given by Ampere's integral law.